Hi everybody, my name is Braxton Michel and today we are going to be discussing limits. So when someone usually mentions calculus, they're met with a very cold and stiff air that fills the room. And there is this stigma that only people with math or STEM brains are capable of learning calculus. I took AP Calculus in high school and then again at Southeastern, and this really exposed me to teaching multiple concepts in different ways. Today I will be teaching you a fundamental portion of calculus, the limit. We will be building the formal definition of a limit throughout the lesson. First, we will use an arithmetic approach using numbers and graphs. Second, we will discuss some exceptions with certain graphical behaviors. And then finally, we will be creating the limit existence theorem. So first, we need to consider the function f of x equals x cubed minus 1 over x minus 1. Now, this is a rational function, and we can also notice that there is a whole discontinuity at x equals 1. And we know that because if you were to plug in 1 for the x's, you would get a 0 in the denominator, therefore the function would not exist at that point. So now I want you guys to construct this table here. And what this table represents is our x values as they approach 1. So we see x equals 0.9. 0.9 is close to 1, but it's not there yet. And then we have 0.99, and we're getting closer to 1. And we could continue that trend, but for sake of space and time, we're not going to continue that far. Same thing on the other side. If we have 1.01, that's very close to 1, and we could continue adding zeros as much as we wanted, and we would continuously be approaching 1. And then the same argument here for 1.1, we're approaching 1. And all this is about the intended y value as the x values approach a certain value. So now I want you to construct this table and plug in all these x values. So if you're to plug in 0.9 for x into the equation, you should get 2.7. If you're to plug in 0.99, you were to get 2.97. Now, it may be too early for some of you to recognize a pattern, and granted it's only 2 boxes, but I feel like whenever I put in the boxes on the other side, you're going to notice a pattern here. So if you're to plug in 1.01, you get 3.03. Okay, and if we plug in 1.1, we get 3.31. So, we say that as x approaches 1 from the left, coming this way, and as x approaches 1 from the right, what are we getting close to? And this pattern may be more recognizable if we went closer and closer and got infinitely close to x equals 1. But here, 2.97, that's very close to what whole number? 3. Same thing is true on the right side. 3.03 is very close to what whole number? 3. So we can say here that the limit of f of x as x approaches 1 is 3. Next, we're going to move to a more graphical approach. And we're not going to deal with calculating numbers in a calculator. So this function graphed right here is this same function. And I made the whole very large so you can tell that there's a whole discontinuity there at the 0.13. So this shows that our math was correct here. Now, you may be wondering what this plus and minus sign means whenever you're looking at the limit statement. This means you are looking at the limit of the function as x approaches 1 from the left. The minus sign means the left, or sometimes people call it below. But you will see there's a little arrow here coming from the left. So what is the intended y value of the function as x approaches 1 from the left? And we say that's 3. So we can say that is 3. This is the same thing is true on the other side, just from the right. The plus sign means from the right. So what is the intended y value of the function as x approaches 1 from the right? And you see there's an arrow here, and the function is approaching 3. So without using numbers or a calculator, we found that the limit of f of x as x approaches 1 equals 3. Now we're going to look at some graphical exceptions. these two functions, we have f of x equals 1 over x squared, and g of x equals sine of 1 over x. And we're going to ask the question, as x approaches 0, what happens? So here, x approaches 0. Our function is growing infinitely large. It's going towards infinity. So if we were to write a limit statement for that, that limit would not exist, because this is growing infinitely large, like I said. So it would be infinity. Well, one of the rules for a limit to exist is that what the limit equals must be real and finite. And infinity is not finite nor real. It is a concept, not a number. So that talks about the first exceptionality. The second exceptionality for g of x equals sine of 1 over x, as x approaches 0, we see that sine of x has this oscillating behavior. And I know it can be hard to see, but if you're to think of a normal sine graph or cosine graph, it's oscillating. It looks like a wave. Well, whenever you put a rational function in the operator part of the sine function, it becomes this odd mess of squiggly oscillations. And we really can't tell where it goes from this picture, but if you're to zoom in, we see that it will continuously oscillate for infinity. They'll get closer and closer and closer together, so it doesn't approach anything. There is no limit for it to approach. So now that we've discussed all three of these criteria, we have built our limit existence theorem. Our first portion, the function must equal L. So right here, we can look at this criteria and go here and say, oh, f of x did not equal 3, therefore that limit does not exist, D and E. Now if we look at this part, and like I already said, I already gave it away, L must be real and finite. So as I said, infinity is neither real nor finite. Therefore, by the second criteria, this limit does not exist, D and E. All right, now if we go to the third criteria, the limit of f of x as x approaches c, that's a c, from the left equals the limit of f of x as x approaches c from the right. They have to equal each other, and then also they have to equal this L. So, as we see here, f of x does not equal L. The right and left-hand sides equal each other, that is correct. And the L here is finite and real, but f of x does not equal L. So, now I have a practice problem for you guys. You are going to find the limit of f of x as x approaches 2, where f of x equals x squared. And I drew a graph right here. Now I want you guys, this little three dot triangle means therefore. So therefore, the limit of f of x as x approaches 2 equals what? And then I want you to tell me whether it exists or not. So, pause the video now. Practice it on your own. Okay, so we see that if we approach from the left-hand and right-hand sides, we see that from both sides it approaches 4. So, okay, that's one criteria. Does f of x exist at 2, 4? Yes, it exists. There's no holes or asymptotes or anything like that. So, and does f of x of 2 equal the limit of f of x as x approaches 2 from the left and right? Yes, that's true. That's all true. Therefore, our limit is 4 and it exists. So that was our practice problem. Now for our closing, today you have braved the storm and now know how to find limits using numbers and graphs, and knowing 2 vital exceptions to limits, and now you know the LET, or the limit existence theorem. As teachers, we will encounter some difficult topics in our curriculum, and it is important to remember when dealing with these topics that are perceived as difficult to remain positive. Make sure you use different strategies because everyone is a different learner. The goal is always attainable.